Now, as we all know, nuclear energy, in particular fission and or fusion, is mandatory in order for us to be able to achieve the carbon neutral economy that's targeted for 2050. And as predicted, a large portion, a great portion of the energy production will be due to nuclear energy in order for us to be able to achieve this goal. Now, I'm just going to make a brief introduction to the program. It's not going to take long. It's just going to be for a few minutes, just to introduce you to the scope and objectives of this school. Okay, so as we all know, nuclear energy is of two types. One is fusion. In fusion, we combine light elements to produce energy. On the contrary, in the case of fission, typically by neutron or gamma radiation bombardment, we split large atoms. So joining fusion, that's the if that's the way you produce heat energy, that's called fusion. If you are splitting the atom, that's called fission. And again, typically in the case of fusion, we have light isotopes. In this case, different isotopes of hydrogen, at deuterium, at tritium. Typically through the fusion reaction, we generate a large amount of heat, and that heat is typically converted to steam, and through a steam turbine, the energy is converted to electricity. That's the generator. And this is, most of you must have seen this. In the horizontal axis, we have the mass number of the isotope. And in the vertical axis, we have the binding energy per nuclear particle in MeVs. As you see, fusion produces much higher, much larger amounts of energy as compared to fission. This is the delta E. If you combine small elements, hydrogen, helium, for instance, this is the delta E. The mass gap that one can achieve. Like around maybe 4 or 6, MeV, per fusion, can be obtained. But on the contrary, if you look at the fission side, take for instance one of the fissile materials, uranium-235, the yield is much less. This is the delta E, that you see. It's much less, compared to fusion. There are several approaches, that has been tried over the years, or maybe 50 years or so, to obtain fusion energy. One of them is the most popular one is the magnetic confinement. Another one is the inertial confinement. But the approach that we are going to focus on more, in this school will be lattice-based confinement. This approach to fusion energy has recently, in the recent years, in the recent decade or so, has been more popular, as opposed to the magnetic confinement and inertial confinement. And I'll cite, the reasons for this shortly. There are a number of examples of magnetic confinement experiments. One of the most recent ones is the MIT SPARC program. And the most popular, all of you must have heard about, is the ITER, international program in France, that attempts to obtain magnetic fusion, magnetic confined fusion. And billions of dollars up till now have been spent with the participation of numerous countries, maybe 20 or so countries in this program, have generated some results, but not the required efficiency. The Q factor, as we call it, has not been achieved up till now. There are numerous engineering problems with this approach. This chart, depicts magnetic confinement-based experiments that have been conducted up till now. Most of them has converged to the ITER program, International ITER program, and then there recently, in the past decade or so, there has been a divergence, of these programs to different international authorities. European Union, for instance, has started a demo program. Japanese, similarly, Chinese and Koreans now they have separate magnetic confinement-based demonstration programs. The second approach is referred to as the inertial confinement fusion. And the most prominent example of this is the National Ignition Lab, or National Ignition Facility, that's located in the United States at the Lawrence Livermore National Lab. In this approach, beams of lasers, high energy laser beams are concentrated or converged on a sample of, again, light materials, proton, light elements. And that's the way, they have been trying to achieve inertial confinement fusion. And it is again depicted in this. A Q value of larger than 1 has been obtained through this experiment in the recent years. However, it's still inefficient, and the energy that's obtained through this experiment is for very short durations, in the order of milliseconds, for very small samples. So if you include all the energy that's spent on the laser beams and other auxiliary equipment, the efficiency of this system is very, very small. Only small, very small, compared to the total energy spent is obtained through this experiment. I'm not going to go through details of the experiment. Maybe some of our lecturers maybe talk about these probably in more detail, but it's also we can say has a lot of engineering problems, and it's not a failed approach, but almost close to failure, similar to the magnetically confined fusion. As opposed to all of these, recently, in the past decade or so, another approach has become very popular, and especially in European Union countries. I attended a conference, it was an online conference 2 weeks ago regarding this. And there are quite a few groups in European Union, as well as NASA in the United States, working on this. This is a different approach that is promising as compared to the other two fusion approaches. And in this case, what we have is we have typically a lattice, metal lattice of atoms, and the fusion material, the elements that we'd like to fuse with, deuterons, or in some cases boron 10 or boron 11, is embedded inside this metal lattice. And this lattice is bombarded at different energies, typically at lower energies, making use of the resonances that's natural or inherent in the fusion material. And the generated heat, when the radiation energy is converted to electricity. So the focus of our program will review all the other approaches to fusion, but our focus will be this lattice confinement fusion in this series of lectures. So just to give you a summary and overview of what we intend to do, Today, on the first day of the program, we'll have a general introduction to fusion technologies and a general review of nuclear physics. And the second day will include nucleosynthesis. We'll start with nucleosynthesis because fusion reaction, the largest fusion reactors in the universe are stars. The star, the energy that's emanating from the stars are due to nucleosynthesis. So we'll try to explore this. And then we'll switch to low energy fusion reactions. There are three types of low energy fusion reactors, the reactions that we can consider: direct, compound, and resonance relations. And all these, will be looked into. In addition, we'll talk about computational frameworks. What kind of tools and utilities we have to do computation analysis of these fusion reactors. On day 3, we switch to particle detectors and associated software applications. Again, in order for us to be able to validate and monitor the fusion reactors, particle detectors are very important. And typically, we use software utilities like Azure R and Giant, to do this kind of analysis. But the analysis in this case mostly will involve computing cross sections of these reactions, the probabilities of achieving these fusion reactions using the detector data. The data collected out of this particle detectors will be used to compute these cross-section computations. And this is going to be introduced on day 3. On day 4, we'll talk about the plasma physics for fusion, because especially in particular in the case of magnetically confined fusion, plasma physics, is very crucial because the phase of the material is in plasma. So we need to be able to understand the electrodynamics of this plasma under the magnetic confinement. And we'll have advanced topics. We'll have a contribution from MIT. MIT has a very large group of fusion research. So we'll have some introduction to this program through a contribution, an online contribution. Similarly, from Tohoku University, we'll have a contribution. The 5th day, we'll again continue with advanced topics, and these advanced topics will typically include the research programs that are related to lattice confinement fusion in different parts of the world. We'll have some presentations from the Polish group and from George Washington University. They will talk about their experimental results, the kind of detectors they use, and in particular, what we call the screening effect of the electrons on fusion reactions. It will be a very important concept. So I stop here and give the floor to the experts of this topic, where we'll learn about in more detail, the different concepts and approaches to fusion. Just one more point as to the objective of this series of lectures. What we intend to do in TÜBİTAK, Fundamental Sciences Research Institute, as a result of this series, is to be able to form a group of researchers for us to be able to pursue meaningful research on fusion technologies, and again, in particular, the promising approach, recent approach that we refer to as the lattice confinement fusion. And I thank you all for joining us and coming from long distances to participate and be part of this program. I also would like to extend my thanks to all the organizers, contributors, scholars participating and contributing to this program. Thank you.